Okay, today let's have a look at chapter 3, curve sketching. Today we're going to have a look at lesson 1 of chapter 3, which is about monotonicity, local extrema, global extrema, and critical points. Okay, first let's have a look at the learning goals of today's lesson. After this lesson, you are expected to be able to understand the increasing and decreasing behavior of a function on an interval. Then find the increasing or decreasing intervals of a function by analyzing the derivative of this function. Understand local or global extrema, critical numbers, and critical points of a function on an interval. And find local or global extrema of a function on an interval, and then solve real-world problems involving monotonicity, local or global extrema of a function. So let's have a look at the key points one by one. Okay, first, the monotonicity, which is about the increasing or decreasing behavior of a function. So basically, the concept of a monotonicity describes the increasing or strictly increasing or decreasing or strictly decreasing behavior of a function on an interval. A function f(x) increases on the interval if fb is greater than or equal to fa for all greater than a, where a and b belongs to some interval I. If fb is strictly greater than fa for all b is greater than a, then we say the function is said to be strictly increasing. Conversely, if a function f(x) decreases on an interval, conversely, a function f(x) decreases on an interval I if we have fb is less than or equal to fa for all b is greater than a, with a and b belongs to this interval I. If fb is strictly less than fa for all b is greater than a, then we say this function is strictly decreasing. So the concept of increasing, decreasing, or strictly decreasing, strictly increasing are illustrated in the following 5 graphs. So in the bottom left, we can see that for any a is less than b, we have fa is smaller than or equal to fb, right? Therefore, in this case, we say f(x) is increasing, but in this case, not strictly increasing on the interval, on the open interval m to n. For the second function, as we can see here, for any a is less than b on the interval m to n, we all have fa is less than fb, right? Therefore, we say f(x) is increasing and also strictly increasing on the open interval m to n. So in the third graph, we say that for any a is less than b in this interval from m to n, we all have fa is less than or equal to fb, right? Therefore, in this case, we say f(x) is decreasing, but not strictly decreasing on this open interval from m to n. In the fourth graph, as we can see here, for any a is less than b in this interval from m to n, we all have fa is greater than fb. Therefore, we say f(x) is decreasing and also strictly decreasing on the open interval from m to n. And in the last graph, apparently, this is not monotonic on m to n. That means it's neither increasing or decreasing on this open interval m to n, right? Any questions? So this is a concept of increasing or decreasing behavior of a function on open interval. Okay, next, let's have a look at the connection between the monotonicity and the derivative of a function. So if the derivative f prime of a function fx satisfies the derivative of fx is greater than or equal to 0 on an open interval a to b, then fx is said to be increasing on a to b. Understand? This means we can use the first derivative to determine if a function is increasing or not. Okay, you need to be careful here. The reverse statement is not necessarily true. Okay, that means, for example, if the function, for example, let's have a look at this function, fx equals x to the power of 1/3. Apparently, this function is increasing everywhere in the domain, right? Including at the point where x equals 0. But when x is 0, the derivative of this function is not defined. Therefore, the reverse statement is not necessarily true. That means if you know a function is increasing in some open interval, that does not necessarily mean the first derivative is always greater than or equal to 0, okay? Because if you look at this example, the derivative also can not exist, right? Careful with the statement here. The reverse statement is not necessarily true. Okay, next, if the derivative f prime x of a continuous function fx satisfies the first derivative of this function is strictly greater than 0 on the open interval from a to b, then we say fx is strictly increasing on the interval from a to b. Understand? And also be careful with the reverse statement. Reverse statement is not necessarily true either. Okay, I'll give you some time to have a look at this connection between the monotonicity and derivative of a function. So basically it tells us you can determine the monotonicity of this function using the first derivative, right? Do you have any questions? Any questions? No? Okay, then next, let's have a look at the connection between monotonicity and derivative of a function, part 2. Okay, similarly, we have the following statements. If the derivative f prime x of a continuous function fx satisfies that the first derivative of fx is less than or equal to 0 on an open interval from a to b, then fx is decreasing on the interval from a to b. Again, be careful with the reverse statement. The reverse statement is not necessarily true. For example, if we consider the function fx equals negative x to the power of 1/3, this function is decreasing everywhere in the domain, right? Including at the point where x equals 0. But when x equals 0, the derivative of this function is not defined. So the reverse statement is not true in this case. And also similarly, we have if the derivative f prime x of a continuous function fx satisfies that the first derivative of fx is less than 0 on an open interval from a to b, then fx is strictly decreasing on the interval from a to b. And still be careful with the reverse statement. Reverse statement is not necessarily true. Okay, do you have any questions? Okay, so can you think of why these two statements are true? Why there is a connection? Why there is a relationship between the monotonicity and the derivative of a function? Okay, remember the derivative is actually measures the instantaneous rate of change, right? If at any point the instantaneous rate of change is either 0 or greater than 0, this means this function keeps increasing at any point, right? Or at least the function is not decreasing, right? Therefore, we have the relationship between whether this function is increasing by only considering its derivative, right? So similarly, we can also determine whether this function is decreasing by considering its first derivative, whether that's smaller than 0 or equal to 0, right? So that's why we can determine the monotonicity of the function on the open interval by checking its first derivative. Okay, then let's have a look at example. Find the open intervals of strict increase and strict decrease for the function defined by fx equals 2 times x to the power of 3 plus 3x cubed, 3x squared minus 36x plus 5. Okay, I'll give you 5 minutes to have a look at this question, okay? Okay, have you finished? Okay, so basically, before we solve this question, I need to mention that in this course, by default, for such a question, we need to find the largest possible open interval where this function is increasing or decreasing, okay? Otherwise, actually, there are unlimited number of increasing or decreasing intervals if you can find one, right? Any subset of the open interval is also a decreasing or increasing interval for this function. So in this course, by default, we find the largest possible open interval where the function is increasing or decreasing for similar questions like this. Okay, so basically first we need to find, we can find this first derivative, right? So so f prime x, the first derivative of this function is 6x squared plus 6x minus 36, right? So in order to find this strict increase interval, we need to let f prime x greater than 0, right? If you can find any interval that the first derivative of f(x) is greater than 0, then that interval is strict increasing interval, right? Okay, so this is equivalent to 6x squared plus 6x minus 36 is greater than 0, which means x squared plus x minus 6 is greater than 0, right? So this question actually converts to a question that to find any interval that makes this quadratic function greater than 0, right? So we can check that by using its graph. So apparently this is a quadratic, the left side is a quadratic function, which is opening up, and there are 2 zeros because it can be factorized to x plus 3 times x minus 2 greater than 0, right? Therefore, we know it's opening up, and there are 2 zeros, which are -3 and 2. So this function is greater than 0 means your independent variable x should be either to the left side of -3 or to the right side of +2. Therefore, this is equivalent to x is either less than -3, or x is greater than 2, right? Therefore, we know the strict increasing intervals there are 2, right? One of them is from -∞ to -3, and the other one is 2 to +∞. So there are 2 increasing intervals. Do not combine them, okay? Because this function, if you combine these 2 intervals, the combined interval is not necessarily increasing, okay? So just remember there are 2 intervals, not 1. Okay, so if you want to find the strict decreasing interval, again, the method is similar. Check which interval can make f(x) is less than 0, right? And we can check that by looking at the graph again. So that interval is from -3 to +1. Therefore, we know the interval from -3 to +1 exclusive. This interval is the decreasing interval of this function, right? Okay, so let's check a proper writing of the solution here. First of all, determine the derivative at prime x, then graph it. So the graph of the derivative of this function looks like this. So we can see from the graph that f prime x is greater than 0 on 2 intervals, which are -∞ to -3 and +2 to +∞. And f prime x is less than 0 on this interval from -3 to +2. Therefore, there are two open intervals of streak increase, which are -infinity to -3 and +2 to +infinity. And there is only one open interval of streak decrease, which is -3 to +2. You understand? Okay, I'll give you some time to have a look at the solution here. Any questions? Okay, if you don't have any questions, let's consider another example. The temperature of a person with a certain strain of flu can be approximated by the function Td equals -5/15d squared plus 15/9d plus 37, where d is between 0 and 6, exclusive. Uppercase T represents the person's temperature in degrees Celsius, and D is the number of days after the person first shows a symptom. During what interval will the person's temperature be increasing? Okay, so it basically asks you to find any interval the person's temperature is increasing, right? Okay, I'll give you 5 minutes to have a look at this question here. Okay, so let's have a look at the solution of this question. So technically speaking, there is a ambiguity. This question is a little ambiguous because it does not specify whether this is a strictly increasing or just increasing, right? So in this case, both of the results are acceptable, but before you land on any conclusion, just tell your reader which type of your increasing interval you are looking for. So for example, here, we are looking for any strict increasing intervals. Okay, so we can find its first derivative. If TD equals, if the expression of TD looks like this, we know the derivative of T with respect to D must be -5/9D plus 15/9, right? And tell your reader if you want to find the strict increasing interval. So in order for the interval be strict increasing, we need to find any interval, the first derivative is strictly greater than 0, right? So we can let T prime D is greater than 0, then this gives us -5/9D plus 15/9 greater than 0, right? And this is equivalent to 5D minus 15 is less than 0, which means D must be smaller than 3. Also note that the domain of this function is D is greater than 0 and less than 6. Therefore, we know the function is increasing, while actually strict increasing. So we need to put the keyword here. Actually, this is a strict increasing. This function is strict increasing. Or strictly increasing on this interval from 0 to 3. So in other words, the person's temperature increases or strictly increases. Over the first 3 days, because D denotes the number of days passed, right? You understand? Any questions? Any questions? No? Okay. Then let's see another question. Sketch a continuous function for each set of the conditions given below. Condition A, the derivative of fx is greater than 0 when x is smaller than 0. And the derivative of fx is less than 0 when x is greater than 0. And also the image of fx at 0 is 4. Okay, second condition, the first derivative of fx is greater than 0 when x is less than -1. And when x is greater than 2, the derivative of fx is less than 0 when x is between -1 and 2 exclusive. And f0 is 0. Okay, so in each of the cases, can you sketch a continuous function given this condition? So note here, there are possibly more than one solution for each condition, right? As long as you can give one function that can satisfy this condition, you'll be fine. Okay, so I'll give you 5 minutes to think about this question. Okay, let's have a look at possible solutions. So, okay, so let's have a look at the solution to this question. According to condition 1, f0 is 4, therefore this function must cross this point, right? Before this point, this function is an increasing function because it says the first derivative of this function is greater than 0. So that function is strictly increasing. So you can sketch this function like this. And after x equals 0, the first derivative of this function is strictly less than 0. That means from the interval, in the interval from 0 to positive infinity, this function is strictly decreasing, right? So we can sketch this function like this. And as to the second condition, first of all, we know f0 is 0. That means this function crosses the origin point here, 0, 0. And before x equals -1, this function has first derivative greater than 0. That means from negative infinity to -1, this function is strictly increasing, right? And after that, we know one axis between -1 and +2. The first derivative is less than 0. Actually, strictly less than 0. Therefore, we know from -1 to +2, this function is strictly decreasing, which means this function should look like this here. Second section look like this, right? And after that, when x is greater than 2, this function has first derivative strictly greater than 0. This means from the interval, in the interval from +2 to positive infinity, this function is strictly increasing like this, right? So there are 3 sections in this function. First, strictly increasing, then strictly decreasing, then strictly increasing again. And also crosses its origin point. Any questions? Of course, the exact shape of the function does not necessarily look like this. Okay, this is just one possible solution. There might be an unlimited number of solutions. For example, you can also draw straight lines. You can also draw straight lines like this. Okay, that's also fine. Straight line, straight line, straight line. That's also fine. Okay, any questions? Okay, if no questions, let's take a 10 minutes break. And after that, we'll have a look at the next key point, which is local extrema and global extreme. Okay, and take a 10 minutes break now. Okay, let's continue our lesson. So next, let's have a look at the concept of local extrema and global extrema. So sometimes if you have a word just extrema without local or global, by default, that means global extrema. So that's why I use the parentheses here, okay? We only have the word extrema. By default, that means global extrema. Okay, first of all, let's have a look at the concept of local maximum and local minimum, which are summarized to local extrema. So fx is called a local maximum if there is an interval, an open interval a to b, with x is between a and b, and fx is greater than or equal to fz for every z in the open interval a to b. In this case, the point fx is called a local maximum. On the contrary, the point fx is called a local minimum if there is an interval a and b with x is between a and b and fx is smaller than or equal to fz for every z in this open interval a to b. Any questions? Okay, so this is the concept of local minimum or local maximum. And local minimum and local maximum are summarized to one word, which is local extrema, also known as the turning points. So basically, a local extrema could be either a local minimum or local maximum. Okay, next, let's have a look at the global extrema, which might be a global minimum or a global maximum. Global extrema is also known as absolute extrema. Okay, so let's have a look at the concept of global extrema, which is stated here. A function has an absolute or global maximum at a if fa is greater than or equal to fx for all x in this domain. The maximum value of this function is fa. The function has an absolute minimum at a if fa is smaller than or equal to fx for all x in the domain, or in some interval. The minimum value of this function is fa. So that's basically the concept of global extrema, right? So here on the left side, we have a graph shows the concept of local extrema and global extrema. As shown here, suppose the curve of fx is highlighted in blue. Then this point here this point here is called the local maximum, right? Because by definition, we can see that there exists a open interval around in the vicinity of this point, such that for every z in this open interval, we have fx is greater than or equal to fz, right? So this point here is called local maximum. Also, this point here is also called local maximum. And this point here is local minimum. And along this curve, the highest point is here, right? So this point is not only the local maximum, but also the global maximum along this curve. And is there any global minimum? The answer is no, because if the curve of this function extends indefinitely to the positive infinity, we know that this function, the global minimum of this function is actually negative infinity, right? Or we say there is no global minimum at all. You understand? Okay. Any questions? Okay, no? All right, let's see the next concept. The connection between local extrema and the derivative of a function. Actually, we can check if a point is the local extrema by checking its first derivative. Okay, so let's have a look at the concept behind this. Given the graph of a function fx, a point is a local maximum if the y coordinates of all the points in the vicinity are less than the y coordinate of the point. So basically, local maximum looks like this, right? So if you have a curve like this point here is the local maximum. Algebraically, if the first derivative of fx changes from positive, so that's positive before this point, right? To 0, so at this point, first derivative is 0, and then to negative. So you can see here, after this point, the first derivative is always negative. So algebraically, if the derivative of fx changes from positive to 0, then to negative, as x increases from x is smaller than a, then to x is greater than a. Then we know the point here, which is AFA, is a local minimum. And A is called the local maximum value. Similarly, we have if a point, we have a point is a local minimum if the y coordinates of all the points in the vicinity are greater than the y coordinate of the point. Basically, if you have a shape like this, then this point is called local minimum, right? If the first derivative of fx changes from negative to 0, then to positive as x increases from x is smaller than a to x is greater than a, then the point AFA is called a local minimum, and A is called local minimum value. So note here, the local maximum and local minimum values of a function are also called local extreme values or local extrema or turning points. A function has an absolute maximum at A if Fa is greater than or equal to Fx for all x in the domain. The maximum value of the function is Fa. The function has an absolute minimum at A if Fa is smaller than or equal to Fx for all x in the domain. The minimum value of the function is Fa. You understand? Any questions? All right, if you don't have any questions, let's have a look at some examples. Okay, see this example here. Find all local maximum and minimum of the function fx equals x cubed minus 12x minus 3 on this interval from -3 to +4 inclusive. Okay, I'll give you 5 minutes to think about this question.
到极值的目标条件。
Okay, let's have a look. Okay, let's have a look at the solution together. So according to our discussion previously, you need to check first the first derivative of fx, right? F prime x equals 3x squared minus 12. So we can let the first derivative of fx equals 0. Then we solved x can be either -2 or +2. Also, you should consider whether the first derivative changes sign in the vicinity of these 2 points, right? So first of all, we check when x is smaller than -2. We know that fx is greater than 0, right? And when x is between -2 and +2, according to the graph of the derivative function, we know f prime x is less than 0, right? Okay, therefore we see when x is smaller than -2, first derivative is greater than 0, and when x is greater than -2, first derivative is smaller than 0. Therefore, we know the first derivative does change sign before and after x equals -2, right? And at x equals -2, the first derivative is 0. Therefore, we know the local maximum x equals -2 is the local maximum point. Therefore, we need to calculate f -2, which gives us 13. Therefore, we know the point -2, 13 is a local maximum point. Also, according to the graph of the first derivative, we also know when x is greater than 0, the first derivative is greater than 0, right? And when x is less than 2, the first derivative is smaller than 0. Therefore, we know the first derivative changes sign from negative to positive before and after x equals 2, right? So this function achieves local minimum at x equals 2. Then we calculate the image of fx at x equals 2, which gives us -19. Therefore, we know the point 2, -19 is the local minimum. Have any questions? So ensure you check 2 things. First, at local minimum or local maximum, your first derivative must be 0, right? Second, before and after the point that makes the first derivative be 0, you need to check whether the first derivative changes sign at this point. If it does not change sign, that means the point is not local minimum or local maximum, okay? Any questions? All right, then let's have a look at other related concepts, such as critical number, critical point, and the method to find global extrema. Okay, first of all, critical number. Critical number of a function is a value a in the domain of the function, for which either the first derivative at x equals a is 0, or the first derivative at x equals a does not exist. Okay, there are 2 conditions. If the first derivative is 0, or the first derivative does not exist at this point x equals a, then this point is called critical. This number is called critical number. And if a is a critical number, the point AFA is called a critical point. Of course, sometimes FA does not exist either, right? Okay, next, in a closed continuous interval, the global or absolute extrema can only be achieved at critical points or endpoints. To determine the global maximum and the minimum values of a function in a closed continuous interval, we can apply the following procedures. The following procedures is the methods we can use to find the global extrema. First of all, we can find all the critical numbers, if any. Second, substitute the critical numbers into that function. Then substitute the x coordinates of the endpoints of the interval into that function. Then find global extrema value of functions from the function values in step 2 and 3. Last, find the coordinates of the global extrema. Okay, so you should also note that if the interval of interest is not a closed continuous interval, the method is similar, but we might need to use other methods such as analyzing the signs of derivative. Okay, if you don't have any questions, so let's have a look at some examples to illustrate how we can find the global maximum and minimum of a given function. So consider this example here. Find all global maximum and minimum of the function fx equals x cubed minus 12x minus 3 on the interval from -3 to +4 inclusive. Okay, I'll give you 5 minutes to have a look at this example here. Okay, let's have a look at the solution of this question. So first of all, we find the first derivative of this function, which is 3x squared minus 12. Then we find the critical numbers. We let the first derivative be 0 and solve this function in terms of x. So that gives us x is either -2 or x equals 2. So note here, there is no point such that the first derivative does not exist. Therefore, the only two critical numbers are x equals either +2 or -2. Then we examine the local extrema at we examine the local extrema that occurs at x equals -2 and x equals 2, and also the endpoints of the interval at x equals -3 and x equals +4. Evaluate fx for each of these values. First of all, f -3 equals +6. Then f -2 equals 13. Then f +2 equals -19. f4 equals +13. Then we know we can compare these values to determine the global extrema, right? So the absolute maximum value is 13. It occurs twice at a local maximum point when x equals -2 and at the right endpoint. The absolute minimum value is -19. It occurs once at the local minimum point when x equals 2. Therefore, we have two global maxima, which are -2, 13 and 4, 13, and one global minimum, which is 2, -19. Any questions? All right, if you don't have any questions, let's see another example. So let's consider is this a real world problem here? The surface area of cylindrical container is to be 100 centimeters square centimeters. Its volume is given by the function V equals 50r minus pi r cubed, where r represents the radius in centimeters of the cylinder. Find the maximum volume of the cylinder if the radius cannot exceed 3 centimeters. Okay, again, I'll give you 5 minutes to think about this question by yourself. Okay, if you have finished, let's have a look at the solution. Okay, first of all, we find the first derivative of v with respect to r, right? R is independent variable here. V prime equals 50 minus 3 pi r squared. Okay, then we find the points that can make this first derivative be 0, which solved r to be square root of 50 over 3 pi, which is approximately 2.3. Also note that there is no value of r can make this first derivative not exist. So and because r is greater than or equal to 0, so the only value of r that can make the first derivative be 0 is approximately 2.3. There is only one critical point when the radius is approximately 2.3 centimeters. Then we can substitute r equals 2.3 and the endpoints r equals 0 and r equals 3. So note here, the closed continuous interval here is from 0 to 3, right? Therefore, we substitute the critical points and the two endpoints to that equation. V equals 50r minus pi r cubed. Then we find V0 is 0. V2.3 is about 76.8. And V3 is approximately 65 over 0.2. Then we know the largest number should be the global maximum, right? If the radius cannot exceed 3 centimeters, the maximum volume is approximately 76.8 cubic centimeters. The radius of the cylinder with maximum volume is approximately 2.3 centimeters. Any questions? So this is how we can find the global maximum by checking the critical points and the endpoints. Any questions? Okay, if you have no questions, that's the end of today's class. Before you leave, let's give the summary of today's lesson by revisiting today's learning goal. So after this lesson, now you should be able to first understand the increasing or decreasing behavior of a function on an interval. Second, find the increasing or decreasing intervals of a function by analyzing the derivative of this function. Third, understand local or global extrema, critical numbers, and critical points of a function on an interval. Then find the local or global extrema of a function on an interval. And last, solve real-world problems involving monotonicity, global or local extrema of a function. Okay, so any questions here? If you don't, this is the end of today's class. And remember to complete the homework on Google Classroom and submit them on time, okay?